Welcome to The Sleepy Scientist, where the universe unravels gently and curiosity drifts quietly into dreams. Tonight, we're setting off on a slow, soothing journey to one of the most unusual places in all of space, the dense heart of a collapsed star. These remnants are what's left behind by once brilliant giant stars that lived gloriously, died spectacularly, and left something behind that's so dense, so strange, and so subtly powerful that even space and time bend gently around. Neutron stars, tiny, heavy, and mysterious. They challenge understanding and spark wonder. So wherever you are, perhaps curled up in bed, wrapped in a blanket, or floating in that peaceful space just before sleep, I hope this helps you settle in for the night. If it doesn't quite send you to sleep, at the very least you'll come away with a bit of astrophysics. That's the delicate risk of making relaxing videos that are maybe just a little too fascinating. If you're enjoying the experience already, a gentle like or a quiet subscribe would mean a lot. That way you won't miss the next cosmic bedtime story. And if you're still awake by the end, I'd love to know where you're watching from and what time it is in your corner of the cosmos. Leave a comment. If you're not fast asleep, now take a deep breath, find your comfort. The stars have exploded, but all is calm. This video is intended for educational and relaxation purposes. It is not medical advice, diagnosis, or treatment. For health-related concerns, including an unusually strong love for neutron stars, please consult a professional. Stellar beginnings before a neutron star is born. Before the collapse, the cataclysm, and the crushing density, there's just a cloud. A wide, quiet nursery, not made of bricks or stone, but of gas dust and the remains of long-dead stars. These are stellar nurseries. If you zoom out far enough, they look like delicate wisps drifting through the dark. But inside, they are anything but still. Gravity is at work quietly, persistently. A star doesn't begin with a bang, but with a slow sag. Over time, particles in these molecular clouds draw together under gravity's invisible pull. Imagine grains of sand gently rolling together on a trampoline. As mass gathers, gravity increases, drawing in even more material. It's a feedback loop that ends with a spark. Eventually, a dense, hot core forms, dense and hot enough to start nuclear fusion. That's the moment a star is born. Hydrogen atoms begin fusing into helium, releasing energy in the process. That energy pushes outward, countering gravity's inward force. The result is a delicate balance, a glowing star held in quiet tension. Suspended in the vastness of space, life and death of massive stars, but not all stars are the same. Some are small, quiet red dwarfs, burning slowly for trillions of years. Others, like our sun, live moderate lives, about 10 billion years of steady warmth. Then there are the giants. These massive stars, the future parents of neutron stars, burn hot, live fast, and die young. They're dramatic, intense, and frankly, exhausting. To become a neutron star, a star needs to start with at least 8 times the mass of our sun. Some stars begin life dozens of times heavier. These stellar titans consume their fuel with urgency, first hydrogen into helium, then helium into carbon, then carbon into oxygen, and so on. Each stage goes faster than the last, like a fire fed with pure oxygen. Eventually, the core reaches iron, and that's where everything changes. Iron is different. Unlike lighter elements, fusing iron doesn't release energy, it requires energy. It's the end of the road. Fusion stops. The star's engine stalls. With no outward pressure left to resist gravity. The core begins to collapse, appreciating massive stars. But before we move on, it's worth pausing to appreciate these massive stars. They're the great forges of the cosmos. Almost everything in you, the carbon in your cells, the calcium in your bones, the oxygen in your lungs, was created inside a star like this. Billions of years ago. Stars don't just light the universe, they build it. And they do it with style. Massive stars often end in spectacular fashion, shaping clouds of gas, forming binary systems, throwing off strong stellar winds, and pulsing with brightness as their inner layers shift and change. They're a little like cosmic teenagers, brilliant, unpredictable, and destined to transform. So, What makes one of these stars become a neutron star instead of collapsing into a black hole? It comes down to mass. If the collapsing core is too small, it becomes a white dwarf. If it's too large, it forms a black hole. But in between lies a strange middle ground where resistance from tightly packed neutrons halts the collapse. At least for a time, that middle ground is the neutron star. The collapse, from star to supernova, when that core collapses, it happens fast. In less than a second, quicker than a blink, temperatures soar to hundreds of billions of degrees. The outer layers crash inward, striking the core and then rebound in a massive shock wave. That shock is what we call a supernova, one of the most energetic events in the universe. For a moment, a single exploding star can outshine an entire galaxy, fusion's final act for billions of years. A massive star burns like a furnace, fusing lighter elements into heavier ones. It starts with hydrogen fused into helium. The energy from fusion pushes outward, counteracting gravity and keeping the star inflated like a balloon, but hydrogen runs low. The star begins fusing helium into carbon, carbon into oxygen, oxygen into neon, neon into magnesium, magnesium into silicon, and finally silicon into iron. Each stage goes faster than the one before. In its final days, these fusion cycles might last only years, months, or even just days, but iron won't cooperate. Fusing it doesn't release energy, it uses it. Trying to fuse iron is like trying to charge your phone with a dead battery. Nothing happens except rising instability. Once the core is full of iron, fusion stops. Gravity, now unopposed, wins. The star begins to collapse. Birth of a neutron star. Collapse happens in less than a second. Temperatures skyrocket past 100 billion degrees. Under extreme pressure, electrons are crushed into protons, forming neutrons and releasing neutrinos, ghost-like particles that stream away in all directions. This is called electron capture. The core becomes a superdense ball of neutrons, shrinking from thousands of kilometers to just about 20. It's like compressing a mountain into a marble. As the outer layers crash inward at near light speed, they hit the dense neutron core and rebound. It's like trying to crush steel with a pillow. It doesn't budge. That rebound, along with the rush of neutrinos, creates a shock wave. The wave tears through the star, blasting its outer layers into space. This is a supernova, cosmic aftermath. Supernova is an extreme event. For a short time, the exploding star can shine brighter than all the stars in its galaxy combined. The energy released in seconds is more than our sun will emit in its entire life. To an observer, it looks like a sudden brightening in the sky, fading slowly over weeks or months, but inside it's pure chaos. Shockwaves rip through, and the star is shredded. Its material is scattered over light years. The elements formed in its core, carbon, oxygen, calcium, and even iron, are flung into the cosmos. Final reflection: from a quiet cloud of dust, a star is born. It lives balancing gravity and fusion in an elegant cosmic dance. But nothing lasts forever. For the most massive stars, that balance ends in seconds, followed by an extraordinary explosion, a supernova, a neutron star, a calm remnant of ancient violence. So next time you look up at the stars, remember, some of those gentle twinkles are the quiet survivors of cosmic collapse. They've seen their cores implode, their outer layers torn away. Now, they spin silently in space, dense beyond comprehension, holding secrets heavier than anything on Earth. All of that from a single cloud of dust. These elements will go on to form new stars, planets, and possibly even life. In fact, every atom of iron in your blood came from a supernova. The calcium in your teeth, the oxygen in your lungs, all born in stellar explosions. This is the poetic side of a star's death. It's also cosmic recycling. One star's end becomes the beginning of many new things, but not every part of the star is destroyed. At the center of the explosion, something remains. If the original star was massive enough, at least 8 times the mass of our sun, its collapsed core will survive the blast. Depending on its final mass, it either becomes a neutron star or, if heavier, continues collapsing into a black hole. We'll save black holes for another time. Let's stay with the neutron star, right after the supernova. This newborn neutron star is extremely hot over 100 billion degrees, but it cools rapidly, releasing energy through neutrinos and light. It spins quickly, often several times per second, and its magnetic field grows incredibly strong. In just a moment, the gentle fusion glow of a living star is replaced by a dense, spinning magnetic remnant compressed tighter than anything else in the universe, short of a black hole. From the outside, it's hard to imagine how violent this process is. But if you were a neutrino created in the heart of that collapsing core, you'd be ejected at nearly the speed of light, passing effortlessly through the rest of the star, through the explosion, and out into space through planets, moons even people, because neutrinos rarely interact with matter, and yet trillions of them pass through your body every second. That's not poetic, it's simply a quiet fact of everyday life. The explosion also sends ripples through space-time gravitational waves. These are tiny distortions in the fabric of the universe radiating from the dying star. We've only recently developed the tools to detect them, but they reveal cosmic events light alone cannot. Supernova are rare in our galaxy, perhaps only one per century, but their light can be seen across vast distances. Some of the earliest recorded guest stars were actually supernova. Ancient astronomers in China, Japan, and the Middle East documented bright new stars that appeared for weeks before fading away. One supernova, observed in the year 1054, left behind the Crab Nebula, still visible through telescopes today. At its center spins a pulsar, a neutron star born in that ancient explosion, from calm beginnings to a catastrophic end. A massive star lives a long, steady life fusing elements for millions of years, only to collapse and explode in its final moments, scattering its remains into space. It's strange that such destruction leads to so much beauty. But the universe is full of paradoxes, violent ends that bring new beginnings, stillness formed out of chaos. At the center of it all, a compact, quiet remnant holding on to secrets forged in fury. When a massive star dies in a supernova, most of its outer layers are thrown out into space, becoming drifting clouds, raw material for new stars and possibly planets. But the core behaves differently. It collapses, yes, but stops, just short of becoming a black hole. What's left is one of the most extreme objects in the universe, a neutron star. So what happens in those last chaotic moments? Imagine we could freeze time, just as supernova is about to erupt. Let's zoom in, not on the explosion, but on the core itself. The star's core has become a dense ball of iron under tremendous pressure. Iron, unlike lighter elements, can't be fused into something heavier without using more energy than it gives off. Fusion stops, gravity wins. In less than a second, gravity crushes the core. Atoms are squeezed so tightly that electrons are forced into protons. These combine to form neutrons, neutral particles with no charge and barely any room between them. This process, called neutronization, fills the collapsing core with neutrons. The entire core effectively becomes a giant atomic nucleus. Neutrinos are released in enormous numbers, carrying away energy. At this moment, the core becomes denser than anything else in the visible universe, hotter than a nuclear blast, and yet it doesn't become a black hole. Why? Because of quantum pressure, specifically neutron degeneracy pressure. This comes from the Pauli exclusion principle, a rule in quantum mechanics stating that no two identical particles can occupy the same quantum state. Neutrons don't like being packed together. They resist. That resistance is enough to halt gravity unless the mass is too great. In that case, the collapse continues into a black hole. But if the core's mass is between about 1.4 and 2.3 times that of the Sun, neutron degeneracy pressure holds firm. The collapse stops. The explosion expands outward. And at the center, something new has formed. A neutron star. Let's pause and consider just how strange this object is. A neutron star contains more than the mass of our Sun, compressed into a sphere just 20 kilometers across, about the size of a city. If you could somehow walk across it, you could do so in a few hours, assuming you weren't crushed, vaporized, or reduced to particles. To picture its density, imagine taking a jumbo jet and compressing it into a sugar cube. A cubic centimeter, roughly the size of a die, would weigh as much as Mount Everest, and yet this object spins quietly in space, cooling and occasionally flashing its intense magnetic beams. Like a cosmic lighthouse dot inside, things only get stranger. The outermost layer is the atmosphere. Thin veil of exotic plasma where light and matter blur. Beneath it is the crust, but don't let that word mislead you. This crust is a layer of super-dense, rigid nuclear material at the top. Atomic nuclei are packed tightly together in a sea of electrons. As you move deeper, pressure increases, forcing protons and electrons to merge into neutrons. This area, called the neutron drip region, features a bizarre mix of nuclear clusters and free neutrons. It's neither fully solid nor fully liquid. Then, there's the so-called pasta layer. Yes, that's the real name. Physicists named it after the shapes these structures resemble: spaghetti, lasagna, gnocchi, and even Swiss cheese. Here, nuclear forces and gravity compete, creating patterns of nuclear matter that are denser than anything found on Earth. This layer may be the strongest material in the universe, over 10 billion times stronger than steel. If you built a bridge out of neutron star pasta, it could probably survive anything except, perhaps, a black hole. Deeper still lies the outer core, where things move from strange to theoretical. At these densities, beyond what any Earth lab can replicate, scientists rely on math and modeling. Most agree the outer core is a superfluid neutrons that flow without friction, a liquid that never slows down, never settles, and moves with eerie perfection. It may also contain superconducting protons, allowing electrical currents to flow without resistance. These quantum behaviors are linked to the odd traits of neutron stars, like pulsar glitches, sudden shifts in spin rate. Think of it as the star having hiccups. Finally, we reach the inner core, where speculation reigns. Some theories suggest that the immense pressure breaks down neutrons into their building blocks, quarks. This would form quark matter, a dense soup of up-down and possibly strange quarks that may exist nowhere else in the universe. Others suggest more exotic particles might form here, like hyperons, with names straight out of science fiction. We don't know for certain. No Earth lab can test it. We can only observe, calculate, and imagine. One thing we do know: neutron stars spin, and they spin fast. Conservation of angular momentum means that as a collapsing star shrinks, it spins faster, like a figure skater pulling in their arms. A massive star that rotated once every few days might, as a neutron star, spin dozens or even hundreds of times per second. These fast-spinning neutron stars are called pulsars. From their magnetic poles, they emit focused beams of radiation. If those beams sweep past Earth, we detect them as rhythmic pulses, like a lighthouse beam flashing across the sea. Neutron stars also have immense magnetic fields. When the star collapses, its field intensifies, like squeezing a magnet tighter. Some neutron stars, called magnetars, have magnetic fields a quadrillion times stronger than Earth's. That's a 1 followed by 15 zeros. Such strength could erase a credit card's data from halfway to the moon. Thankfully, magnetars tend to keep their distance. All of this, the extreme density, the fierce gravity, the strange forms of matter, and the magnetic intensity, is packed into a sphere the size of a city, spinning silently in space. It's easy to forget that these bizarre remnants began as ordinary stars, fusing hydrogen and glowing softly among their stellar neighbors. Now, they sit as dense relics, evidence of the incredible violence that marks the end of a star's life. Neutron stars are strange, yes, but they're also beautiful. They capture physics at its limits and hold secrets we've only begun to uncover. They are the middle children of stellar evolution, not quite stars, not quite black holes, but with a character all their own. And although they may seem distant or alien, we are made of the same matter, literally, the iron in our blood, the calcium in our bones, all of it forged in the fiery deaths that create neutron stars. In a very real way, we are stardust, and maybe that's why we find these stars so captivating. These elements will eventually become the building blocks of new stars, planets, and perhaps even life. In fact, every atom of iron in your blood was born in a supernova. The calcium in your teeth, the oxygen in your lungs, all created in the Cores of dying stars. That's the poetic side of stellar death, it's cosmic recycling. The end of one star lays the foundation for many new things, but not all of the star vanishes. At the core of the explosion, something remains. If the original star was massive enough, at least 8 times the mass of our Sun, the collapsed core will survive. And depending on how massive that core is, it will either become a neutron star or, if heavier still, collapse further into a black hole. We'll leave that darker path for another time. For now, let's stay with the neutron star, right after the supernova. This newborn neutron star is unimaginably hot, over 100 billion degrees. But it cools rapidly, losing energy through neutrinos and light. It also spins incredibly fast, often several times each second, while its magnetic field intensifies dramatically. In just moments, the warm glow of a living star is replaced by a dense, spinning magnetic core, tightly packed and more extreme than anything in the universe aside from a black hole. It's hard to grasp how violent this transformation is. But imagine being a neutrino born inside that collapsing core. You'd be launched out at nearly the speed of light, passing straight through the rest of the star, the explosion, and even through entire planets, because neutrinos rarely interact with matter. In fact, trillions of them pass through your body every second without you noticing. That's not an exaggeration, it's just a quiet, invisible part of everyday life. This colossal explosion also sends ripples through the fabric of space-time. These are gravitational waves, tiny distortions in the structure of the universe. We've only recently gained the ability to detect them, but they provide insights that light alone can't offer. Supernovae are rare in our galaxy, maybe one every 100 years. But their light can be seen from far across the cosmos. Some of the earliest written records of sudden bright stars, what ancient astronomers called guest stars, were actually supernovae. Observers in China, Japan, and the Middle East documented these appearances, sometimes lasting for days or weeks before fading. One supernova seen in 1054 left behind the Crab Nebula, which we can still observe today. At its center is a pulsar, spinning neutron star left behind by the blast. From a slow burn to a sudden detonation, the life of a massive star ends in dramatic fashion. For millions of years, it holds itself together, fusing elements and glowing steadily. Then, in mere seconds, it collapses and explodes, spreading its material across the galaxy. It's remarkable that such a violent event leads to beauty and rebirth. That something so destructive can also be a beginning. The universe is full of these contradictions, explosions that create, deaths that give rise to life, quiet emerging from chaos. At the center of it all, a neutron star, small, dense, and silent, but holding secrets deep within. When a star dies in a supernova, most of its outer layers are thrown out into space, joining clouds of dust and gas, raw material for future stars, and possibly planets. But the core does something strange. It collapses, but not into a black hole, at least not always. It lands in an odd middle ground, creating one of the most extreme objects we know, a neutron star. So what exactly happens in those final moments as the core gives in to gravity? Let's imagine we could pause time, just as the supernova is about to erupt. Focus not on the explosion, but on the core itself, on the atomic level. By this point, the star's core is an iron ball under immense pressure. And as we've learned, iron can't release energy through fusion. It takes more energy to fuse than it gives, so fusion halts. With no outward force, gravity takes over. Fast. In less than a second, gravity crushes the core inward. Atoms are pushed together so tightly that electrons are forced into protons, forming neutrons. This process, called neutronization, turns the core into a dense sea of neutrons. It's like the entire core becomes one massive atomic nucleus, stripped of its usual structure. The neutrinos formed during this transformation fly out, carrying away huge amounts of energy. For a moment, the core becomes denser than anything else in the visible universe, hotter than any nuclear explosion, and yet still not a black hole. What stops the collapse, at least for now, is something called neutron degeneracy pressure. It's a quantum mechanical effect from the Pauli exclusion principle. No two identical Particles, like neutrons, can occupy the same state at once, so they push back. If the mass isn't too great, this pressure halts the collapse. This balance only works for cores between about 1.4 and 2.3 times the mass of the Sun. If it's lighter, it becomes a white dwarf. If heavier, gravity wins and the core becomes a black hole. But in this middle range, a neutron star is born. Let's take a moment to appreciate how strange this object is. A neutron star packs more mass than the Sun into a sphere just 20 kilometers, wide about the size of a city. A single teaspoon of neutron star matter would weigh around 6 billion tons, the same as Mount Everest. You could walk across a neutron star in a few hours, assuming you weren't crushed, vaporized, or turned into a fine atomic mist. Inside, things only get stranger. The outermost layer, called the atmosphere, is just a few centimeters thicker. Chaotic zone of plasma where light and matter interact in extreme ways. Beneath it lies the crust, an ultra-dense shell of packed nuclei surrounded by electrons. As you go deeper, the pressure forces nuclei into strange shapes. Scientists call this region nuclear pasta. These forms resemble spaghetti, lasagna, and even Swiss cheese, shaped by the interplay of gravity and nuclear forces. It may be the strongest known material in the universe, over 10 billion times stronger than steel. Beneath the crust is the outer core, likely made of a neutron superfluid, type of matter that flows without resistance. This is matter in one of the strangest states we can imagine, possibly including superconducting protons and electrons. These components may explain odd behaviors like pulsar glitches, sudden changes in a neutron star's spin. Go deeper still, and the mysteries multiply. Some theories suggest that the pressure breaks neutrons into their fundamental parts, quarks, creating a quark-gluon soup that exists nowhere else. Others propose even stranger particles like hyperons or meson condensates. We can't test these directly. No lab on Earth can replicate the conditions, but observations and models offer clues. What we do know is that neutron stars don't behave like anything else. Their gravity is more than 200 billion times stronger than Earth's. If you stood on the surface, which of course you can't, you'd weigh hundreds of billions of times more than normal. A single step would crush every atom in your body, and yet, despite this extreme pressure, neutron stars are remarkably stable. They can last billions of years, cooling, spinning, pulsing all the while. They're like frozen fossils of physics, patiently waiting to be understood. It's humbling to realize how much we still don't know. We've landed probes on Mars, mapped the human genome, launched telescopes into orbit, but when it comes to neutron stars, we're still guessing. Peering through a cosmic keyhole, trying to understand what's on the other side. And maybe that's what makes them so fascinating. Not just their density or magnetism, but the way they challenge our understanding. They remind us that even the tiniest things, just 20 kilometers across, can hold the universe's biggest questions. So the next time you stir your tea or pass by a hill the size of a teaspoon of Mount Everest, think of neutron stars. Think of nuclear pasta, superfluid cores, and crushing gravity. And then exhale, knowing that for now these extreme objects remain safely tucked away in the quiet corners of the cosmos, dense with secrets, spinning in silence. Some pulsars have companions, white dwarfs, or even other neutron stars, and orbit them in tight, intricate patterns. These systems are especially valuable because their gravitational interactions reveal rich insights. Take the famous Hallstaler binary pulsar. It provided the first indirect proof of gravitational waves. As the two neutron stars orbited, they gradually spiraled inward, just as predicted by Einstein's theory of general relativity. They weren't losing energy through light, but through ripples in space-time. That discovery earned a Nobel Prize and laid the groundwork for the gravitational wave detectors we use today. And then there are pulsar glitches. Occasionally, a pulsar that spun steadily for thousands of years will suddenly speed up just slightly. These glitches may result from starquake shifts in the neutron star's crust or from interactions between the superfluid interior and the solid outer shell. Whatever the cause, the star momentarily stumbles and then resumes spinning just a bit faster than before. A cosmic hiccup, in a sense, Pulsars also play a role in some of the universe's most energetic events. When two neutron stars spiral together and merge, a process that takes hundreds of millions of years, they release a burst of gravitational waves, a flash of gamma rays, and a kilonova explosion. These rare events light up the cosmos and forge heavy elements like gold and platinum. The death of a pulsar can, quite literally, create treasure, but perhaps the most surprising thing about pulsars is how calm they seem. On paper, they're extreme city-sized spheres of compressed matter, spinning hundreds of times per second, emitting radiation through vast magnetic fields. Yet from Earth, they appear as steady, rhythmic beacons like cosmic metronomes marking time in deep space. Some are so precise that we can predict their timing to within a millionth of a second. In the vast, chaotic universe, they offer regularity subtle rhythms, quiet pulses in the dark, and that way they're almost comforting, not loud or dramatic, just consistently present. A tap, a beat, a soft flicker in the night sky. You'll likely never see one directly or hear its signal. But somewhere across the void, a neutron star is spinning just as it has for millions of years and will continue for millions more. Tick, tick, tick. Some neutron stars go even further. As if being incredibly dense, tiny, and fast weren't enough, they push into territory that borders on the absurd. These are magnetars neutron stars with magnetic fields so powerful they make regular neutron stars seem mild. In a universe filled with extreme objects, magnetars stand out. To understand what makes them unique, let's begin with the basics. Every neutron star has a magnetic field created by its rotation and the movement of charged particles. A typical neutron star might have a magnetic field trillions of times stronger than Earth's, which is already enough to disrupt anything that gets too close, but magnetars go much further. Their magnetic fields can be 1,000 times stronger than even that. In numbers, that's about 1 quadrillion Gauss. For comparison, Earth's magnetic field is around half a Gauss. So, a magnetar's magnetism isn't just strong, it's almost inconceivable. If one were placed at the moon's distance, it could erase the magnetic strips on credit cards. Not poetic metaphor, just physics. The magnetism is so intense it affects the very nature of empty space. Quantum electrodynamics kicks in, and the vacuum behaves like a lens-bending light based on its polarization. Astronomers have observed this effect in real magnetars, confirming these are not just theoretical predictions but real phenomena. So how do magnetars form? The current theory is that they're born from particularly massive stars that collapse while spinning rapidly and with high internal magnetism. During the collapse, the shrinking volume compresses magnetic field lines, amplifying the magnetic field to extreme levels. The result is a compact, rapidly rotating star with a magnetic field strong enough to rip atoms apart from a distance, but magnetars don't stay fast. Their extreme magnetic fields act like a braking system, slowing their spin over time. Most magnetars rotate only once every few seconds, slow by neutron star standards, but still faster than most objects in the universe. The energy lost from this magnetic braking heats the surface and powers bursts of high-energy radiation, and this is where things get dramatic. Magnetars are known for sudden flares of X-rays and gamma rays. These flares can release more energy in a single second than the sun emits in 100,000 years. Some are subtle quiet flares called soft gamma ray repeaters. Others are incredibly powerful. The strongest flare ever recorded came from a magnetar about 50,000 light-years away, on December 27, 2004, for a fraction of a second. It was the brightest object in the sky apart from the sun. Had it been just 10 light-years away, it could have severely damaged our atmosphere. Thankfully, magnetars tend to keep their distance. These outbursts are believed to be caused by starquakes. Much like how Earth's crust can shift during an earthquake, a magnetar's crust under immense magnetic stress can suddenly crack. This releases huge amounts of energy, sometimes altering the magnetic field itself. Imagine a star's ultra-dense crust snapping, sending ripples through space-time. That's a magnetar quake. These events are more than just cosmic fireworks. They're scientifically valuable. The energy from magnetar flares travels through space, interacting with gas clouds, affecting star formation, and giving us clues about space-time itself. Magnetars become natural laboratories for high-energy physics and quantum mechanics, yet, despite all their power, magnetars live short, quiet lives. After around 10,000 years, a blink in cosmic time, their magnetic fields fade, the flares stop, and they gradually resemble ordinary neutron stars. Their time in the spotlight is brief but unforgettable. So far, astronomers have confirmed only a few dozen magnetars, though many more likely exist, hidden or too distant to detect. Some are found in supernova remnants, others in star-forming regions. We've even detected fast radio bursts, sudden intense signals that might be tied to magnetars. The mystery continues. Their unique traits have made them a popular subject in science fiction. Sometimes portrayed as unstable cosmic villains, their real story is more nuanced. Yes, they're powerful and dangerous, but they're also surprisingly fragile, cracking under their own stress, fading quickly, and spending most of their lives in quiet solitude. If you could observe one from a safe distance, say, several light years away, you might see a faint glow of high-energy radiation. You wouldn't hear it. But if it flared, you might detect a brief flash, a spike on your instrument, gone in less than a second, leaving you puzzled and your software asking, "What was that?" That's how magnetars behave. They erupt, wind down, and vanish like cosmic phantoms. But in their brief lives, they reveal the raw power of the universe. They're a reminder that nature doesn't need size to be intimidating. Density, magnetism, and a short temper will do, and yet they have a strange kind of peace to them. After the flares and the bursts, they settle, they slow, they cool, they fade. Somewhere in the galaxy, one might be doing exactly that, flaring quietly, twisting magnetic fields and bending light with nothing more than a shrug. Magnetars aren't monsters. They're masterpieces, short-lived, powerful, and unforgettable. From a distance, neutron stars seem still rotating steadily, emitting consistent pulses, but inside they're far from calm. Beneath their rigid surface, something shifts, subtle motions that occasionally disrupt the star's rhythm. These interruptions are called glitches, and they're caused by forces so strange they border on science fiction. But before we explore the strange world of glitches and starquakes, it's worth appreciating just how steady these stars usually are. Pulsars, the spinning neutron stars that beam signals toward Earth, are famously reliable. Some spin hundreds of times per second with extraordinary regularity. Astronomers even use them as natural clocks. A few are so precise that, compared to atomic clocks, their timing differs by only microseconds over years, and then suddenly something changes. The star speeds up just a little. The increase is tiny, just a few parts in a million, but it's noticeable and puzzling. Because in space, spinning objects are expected to slow down over time due to radiation and magnetic drag. So, a sudden increase suggests something unusual is happening. These events are called pulsar glitches. First identified in the late 1960s when the Vela pulsar unexpectedly sped up. They've since been detected in many other pulsars. What causes them? To find out, we have to look inside a neutron star. Its crust isn't like Earth's. It's vastly denser and stronger, but even it has limits. Over time, as the star spins and internal forces shift, stress builds up. Eventually, something breaks. One explanation is a starquake, a sudden shift in the crust. When the crust snaps inward, it brings more mass closer to the star's axis. Like a figure skater pulling in their arms, this causes the star to spin slightly faster. Another explanation involves the superfluid interior, an exotic substance beneath the crust that flows without resistance. It doesn't spin normally. Instead, it forms tiny whirlpools called vortices. These vortices can get stuck to the crust. While the crust slows from radiation loss, the superfluid keeps spinning. Over time, tension builds. Eventually, the vortices suddenly unpin, transferring their angular momentum to the crust. The result, a glitch. Both models, crustal shifts and vortex unpinning, likely contribute, depending on the star's age. Younger neutron stars may glitch due to crustal movement. Older, cooler ones may be governed more by superfluid behavior. Glitches are one of our only clues to the inner workings of neutron stars. Interestingly, after a glitch, the spin rate doesn't stay elevated forever. It usually relaxes, drifting back toward its original pace over days, weeks, or months. The star, in a way, remembers its former rhythm. It settles back like a wound-up toy returning to rest. Sometimes, glitches also change the star's pulse profile, the shape of its beam. This hints that more than just rotation is shifting. The magnetic field might be adjusting, the crust deforming, or the entire star subtly reorganizing itself. There's something almost poetic in that, a dense stellar remnant, still active still, changing not just a frozen corpse but a machine under tension, creaking with memory and movement. And glitches aren't just curiosities, they're useful. By studying them, scientists learn about neutron star interiors, crust strength, and superfluid dynamics. It's like analyzing a cracked bell's ring to understand its metal composition. Then, there's the rarest kind of glitch, the anti-glitch. Instead of speeding up, the star suddenly slows down. These are rare and still not well understood. They may result from a reconfiguration of the magnetic field or a sudden change in the interaction between the crust and superfluid interior. Whatever the cause, they remind us that neutron stars are complex. From afar, they seem like perfect clocks blinking with robotic precision. But up close, they're full of strain, tension, and sudden shifts. They twitch, they adjust. They remember. It's strange to imagine stars with personalities. But the more we study them, the more expressive they seem. Their glitches are like size echoes from collapsed cores that still carry the weight of forces we're only beginning to understand. Neutron stars, by their nature, may be invisible, but in the right light, at the right moment, they reveal more than just themselves. They reveal how far we still have to go.